First of all, welcome everybody. Good morning, afternoon, or evening, wherever you're tuning in from, and welcome to Pixel's webinar, co-hosted with T. Carta, on the role of hyperspectral imaging in aquatic monitoring. My name is Amy Zammit. I form part of Pixel's marketing team, and I'll be moderating today's session. And I'm thrilled to be hosting the session where our speakers will explore how Pixel and T-Carta's technology can help to monitor and protect aquatic environments. We can jump to the next slide. So to give a bit of a brief about Pixel, to those of you who don't know, Pixel is a space data company building a constellation of the world's highest resolution hyperspectral Earth imaging satellites, specifically designed to reveal insights across diverse environments, including but not limited to aquatic systems. Our satellites and analytical tools empower users to process data and access detailed information with precision and ease. Pixel's plan and goal is to build a health monitor for the planet, making it possible to track water quality, detect pollutants, and monitor marine ecosystems. Next slide, please. And we're also joined by T-Carta today. So T-Carta is an industry leader in marine geospatial products and remote sensing applications, specializing in creating data solutions to support environmental monitoring and resource management for aquatic systems. With expertise in satellite-derived bathymetry and benthic habitat assessments, T-Carta's work aligns perfectly with Pixel's mission to support comprehensive environmental insights. Next slide, please. Today, I am joined by two industry experts. Firstly, we have Jeremy Kravitz, Pixel's senior hyperspectral scientist, who will dive into how hyperspectral imaging can enhance water quality monitoring, detecting algal blooms, and support regulatory compliance. We're also joined by David Flanagan, the principal investigator at T-Carta, who will showcase how T-Carta uses remote sensing for benthic habitat assessment, detecting contaminants, and monitoring overall ecosystem health. And lastly, we're also joined by Megan Gallagher, our industry principal at Pixel, who will moderate the panel discussion and Q&A session. So a quick note before we begin. You'll notice you're all been placed on mute, and the chat is disabled to ensure a smooth session. However, please feel free to use the Q&A box at any time, and our moderator will be checking them throughout the session to respond to your questions. Also, the webinar is being recorded and a replay will be available on demand. And yeah, without further ado, we can begin. I'll hand it over to Jeremy to begin the session. Thank you.
Jeremy, you're muted.
Sorry about that. Yeah. Hi, everyone. Thanks a lot, Amy, for that introduction. I'm Dr. Jeremy Kravitz. I'm the lead of the Global Analytics Department here at Pixel. And I'm also the hyperspectral subject matter expert here. And I just wanted to first start talking about what the current state of remote sensing is for aquatic applications and what are some of the current challenges that we face in this industry. One of that being traditionally sensor design has not been traditionally applicable for really kind of small and optically complex water bodies. These are highly spatial and temporally dynamic systems, and they require very advanced sensor optomechanical characteristics. Generally over land surfaces as well and over water bodies, we can have extremely highly variable atmospheric conditions, and as combined with dynamic water signals on the ground, as well as adjacency signals, these can corrupt standard atmospheric correction procedures. And this has been a really kind of exciting avenue of development over the last 10 years or so, is improving the atmospheric corrections over water bodies. And as I mentioned, a lot of the water bodies that we see in coastal and inland areas Sometimes in situ validation can be quite difficult. It's time consuming and it's error prone. And there's actually quite a bit of paucity of ground truth data in some of these more optically and hard to reach aquatic zones. And there's also been a bit of institutional barriers where there's been lack of collaboration and standardization amongst the field due to the multidisciplinary nature of aquatic remote sensing and a lot of the different industries and applications that it can provide. So what necessarily makes hyperspectral so special? So when we talk about hyperspectral imaging, it's such a powerful tool, and why it's such a game changer, especially over water applications, is that if you see here, we have the visible light spectrum, which is basically everything from violet to red, which covers the wavelengths we can actually see from about 400 to 700 nanometers. Now, most of us are familiar with traditional multispectral sensors like Sentinel-2, which shows the bandwidths over here on the left. And these sensors capture just a few broad bands across the spectrum. And each band covers a chunk of wavelengths. So you can get a general sense of what's there, but it's kind of like looking at everything through a set of sunglasses with just a few colors. But now let's compare with the hyperspectral sensors like Pixel's Firefly setup shown over here on the right. Hyperspectral sensors can capture hundreds of super narrow bands, and instead of just a few big chunks, it's like having hundreds of little tiny windows that you can see really fine details. And it's the difference between seeing a rainbow as just red, green, and blue versus seeing every single color in between. So why does that really matter for water? With hyperspectral, we can pick up on really subtle differences that are essential for understanding water quality. For example, we can identify specific types of algae in harmful algal blooms because we're able to see their unique spectral pigment signatures. Or if we're looking at the sea floor, be able to differentiate between different benthic habitat types. Being able not only to differentiate species of seagrass, but also being able to measure their photosynthetic activity and potentially their physiology. Also being able to measure and map coral bleaching events more accurately and at broader scales. And this level of detail also means we can keep a closer eye on things like water clarity, turbidity, nutrient levels, stuff that's crucial for managing water health. So hyperspectral gives us this incredible detail and fidelity that you just don't get with regular multispectral imaging. And as we go on, I'll show you how that detail is being used to tackle some big challenges in water quality monitoring, from algal blooms to benthic mapping. So let's take a little bit of a closer look at what makes hyperspectral imaging such a powerful tool for things like harmful algal blooms. Specifically here, we're looking at the reflectance signature of a cyanobacteria bloom, which is this black reflectance line here in this chart. And also on this chart, each colored block represents the spectral bands of different multispectral sensors, that being Landsat, OLI, Sentinel-2, MSI, MODIS, MERIS, and Sentinel-3 ULCHI. And each of these captures a very limited number of broad bands across the visible to near infrared spectrum. And you can see how each sensor covers some of the spectrum, but there are still some significant gaps where information is missed. And this setup is fine for general monitoring, but it doesn't really quite capture all of the details. And now if you look at the top section there, the yellow bars represent our hyperspectral Firefly sensor. And with these many very narrow bands covering the entire visible to near infrared range, it's far more detailed than the multispectral sensors. And you can resolve much finer details that manifest in the reflectance signatures, such as the ones seen on here. So this curve shows specific peaks and dips, which are unique to a cyanobacteria bloom, which is a particularly harmful algae, which unfortunately is becoming quite common in inland waters around the globe. And if other phytoplankton were present, like diatoms or green algae, we'd see different absorption and reflectant features, especially around the chlorophyll absorption peak around 675 nanometers. And so hyperspectral data lets us differentiate between these different groups of phytoplankton based on some of these really subtle spectral differences. So this is one of the big advantages of hyperspectral data, and it lets us resolve really sudden spectral changes in the environment and identify different phytoplankton groups, giving us really reliable and actionable data for monitoring water quality and addressing issues like toxic algae blooms. So now let's dive into some of the actual key aquatic applications where we see hyperspectral imaging really shining. So This technology offers really unique benefits across different water-related monitoring needs. A few examples being aquatic vegetation mapping, where we can differentiate species and habitats more precisely than really what we've been able to do with multispectral. So this is especially useful for managing ecosystems with high biodiversity, like seagrass meadows or coral reefs. Plus, with hyperspectral data, we get better water column correction, which means clearer and more accurate readings of, and potentially even more optically complex or turbid waters. It also lets us quantify aspects of plant health, things like chlorophyll content and photosynthetic efficiency, which are really critical for understanding ecosystem health. Also for harmful algal blooms and eutrophication, HSI is ideal here because it can really detect early signs of nutrient buildup, which is one of the first indicators of eutrophication. It also enables us to classify specific algal groups more accurately. For instance, if we can tell the difference between a benign algal bloom and a harmful one, like cyanobacteria, based on their unique spectral signatures. And hyperspectral's adaptability to really manage monitoring in different water conditions means we can still gather really reliable data in even challenging and optically complex environments. Then there's also applications in water turbidity and sediment transport where hyperspectral can help us track different sediment sources, whether that's natural erosion, agriculture runoff, or industrial pollution. So we can follow sediment transport pathways, which is really essential for understanding sediment impact on coastal ecosystems. And this capability can really support watershed and coastal management efforts by providing really detailed insights into the sediment dynamics over time. Furthermore, we have industries like coral reef management who could also really benefit. HSI data enables us to map coral species and substrate types at much better accuracies, which is essential for managing biodiversity and understanding reef health. So it's also more sensitive to changes in coral pigmentation, so allowing us to detect coral bleaching earlier before the damage becomes really severe. So monitoring coral health and productivity like this is vital, as some of these reefs are under really increasing pressures from climate change concerns. We also have microplastic detection is also becoming of really increasing concern. So hyperspectral imaging can capture the subtle spectral differences between different types of plastics, helping us to really identify and differentiate microplastics in aquatic environments. And this sensitivity also means we can detect potentially smaller plastic particle sizes that better than we can do with traditional methods. And it works well in complex and turbid waters where plastics might also be mixed with other kind of suspended particulates. This capability is also really becoming pretty critical as microplastic pollution continues to rise around the world and is really impacting ecosystems globally. And also kind of intertwined with benthic mapping is satellite-derived bathymetry, which is essential for supporting coastal management and navigation, as HSI offers enhanced substrate discrimination, which is really essential for accurately mapping the seafloor in shallow waters. It's a little bit more limited in terms of depth penetration than, say, like radar and LiDAR sensors, but where these really succeed is more effectively discriminating benthic types and substrate types better than conventional sensors. And the approach is not only really capable of delivering high accuracies, but also acts as a really cost-effective and scalable way to map underwater topography. Now, traditionally, as I mentioned before, remote sensing of coastal and inland water bodies has been really quite technically challenging. And one of the reasons why is because they're so really optically complex. So this slide breaks down a lot of that complexity of interactions and competing signals that really make aquatic remote sensing quite tricky. And when we're trying to observe water bodies from space, we're not just capturing clear signals from the water itself. Instead, we're dealing with a real mix of influences that we have to disentangle. So the main signal we're obviously interested in from an aquatics perspective is just the signal derived from the water column itself. And this signal is driven by 5 main kind of optical properties, and that being the phytoplankton particles themselves, which could be of varying type and size, the mineral particles, which also could be of varying type and size, colored dissolved organic matter, or CDOM, which originates from the decomposition of plant and animal matter and has really large effects on light penetration. There's also detritus, which is also constitutes non-living organic matter from and from deteriorating phytoplankton particles. And then, of course, we have the water itself, which is actually pretty standard around the world and pretty well known, that signal. We've also got shallow water regions, which then bring in additional complexity with submerged vegetation, coral reefs, other benthic substrates contributing to the water leaving radiance. And then we have the atmospheric correction to deal with as well, which I mentioned, trying to account for the various aerosols and gases present in the atmosphere. And then we even have some sources of signal contamination that we have to deal with, especially with really small water bodies. Some of the most notorious being the adjacency effect, which I mentioned earlier, where photons from a nearby bright land pixels can scatter into the field of the view of the sensor, and can introduce a lot of uncertainty into some of your downstream models. As well as surface sun glint, which is that kind of like mirror-like reflection of sunlight off the water surface when viewed at certain angles, and can really oversaturate the pixels. So this is where hyperspectral imaging, really can make a difference. With its really fine spectral detail, we can separate these really complex signals much more effectively than traditional EO sensors, and really help reduce uncertainties and errors in downstream applications and reporting. So with all that being said, why don't we dive into some actual real-world use cases where we'll have a discussion with our partner, T-Carta, with Dave, who's here, and just go through some of the exhibits of some of the kind of work they do and why they're excited to partner with Pixel and leverage our hyperspectral offerings. So with that, I'll pass it over to Dave, and he can chat a little bit about what they do at T-Carta.
One quick thing before you begin, Dave, I would just like to address the audience. This is going to be a very relaxed sort of discussion. If you guys have any questions, please feel free to put them into the Q&A, and I will be bringing them up during that discussion. So if there's anything you hear that you'd like to know more about, this is definitely your opportunity to ask those questions and get some answers from the experts. And with that, I'll pass it back to you.
Yeah, thanks, Jeremy and Megan. Yeah, so as Jeremy mentioned, water quality can be incredibly dynamic. Jeremy, can you actually go back to the previous slide there?
Yeah.
It switched for me. Oh.
This one.
Oh, the next one. There we go. This one. Anyways, yeah, it's incredibly dynamic, and it changes over scales from minutes to hours versus days to months. It's impacted by tides, water flow such as rivers, and other runoff, and in some instances even wind. So this figure here is showing a Sentinel-2 time series of surface water particulate backscatter in Galveston Bay, Texas. And as you can see, it changes very rapidly, and it's a very dynamic system. So the red here in this figure indicates high quantities of particulate backscatter, and then the blue is lower quantities there. And so when we're doing a project at T-Carta looking at water quality, typically what we do is look at a historical, we do kind of a historical study. So the graphs on the right here show that, looking back in time, we can kind of see how these water bodies change and the different components that we're looking at. And then what we do typically is do a sort of monitoring study as well. So we'll monitor in real time for those folks who want to know what's going on in more of the near term. So in the figure here, I mentioned we're looking at particulate backscatter. So this is really a measure of the amount of suspended particles in the water body, things like sediments and organic matter that Jeremy has mentioned already. And we can also measure other things like chlorophyll A. You can see on the graph here on the right. This is kind of a measure of the amount of phytoplankton in the system and can provide insights about the health of a water body. And chlorophyll typically changes seasonally. However, we can look at the magnitude of those seasonal changes with some of this remote sensing of water quality. And we're also able to combine these indicators. So look at combining particulate backscatter, chlorophyll A, and then create some sort of indices like a trophic state index, where we can actually classify water bodies based on their trophic state and what is actually happening due to the dynamics of that system. Yeah, so moving on to the next slide here, we do a lot of target analysis, meaning that we look at specific areas. So in the top panel here, you see we're looking at specific inland water bodies, specific lakes, and looking at water characteristics of those lakes. I mentioned previously that the water quality is dynamic, but what we can do in order to kind of sometimes get a better picture of what's going on in the system is actually look at monthly averages. So on the bottom here, we have monthly averages of Sentinel-2 in a coastal area. And a lot of times this allows us to get a better picture of the seasonal variability of a system. And sometimes a lot of the folks we work with are looking at, maybe specific events that have happened. And they're looking for, a point in time where maybe some of their seagrass has started to die, their coral reefs have started to decline. And this is a way that we can kind of look at the data and then kind of an easier to digest way and maybe pinpoint when some of those things have started to happen. So as you can see from the last two slides, we've primarily been using multispectral sensors to do a lot of this work. We've shown Sentinel-2 here, but we use pretty much all available multispectral sensors to do this. We kind of fall under we like to say, the more data we have, the more of a story we can tell for a water system. But that multispectral imagery does sometimes limit the specific, indicators or variables that we're looking at in a water system, as Jeremy's mentioned. So what we're really looking forward to is being able to use hyperspectral imagery to look at more narrow band indices and look at specific absorption features of different different phytoplankton species, and really be able to tease out some of the things that are going on in these water systems. Like I said, hyperspectral is something that we're really looking forward to using more and being able to extract more information than we currently can using multispectral sensors.
Yeah, cool. That's great, Dave. Thanks a lot. So T-Carta came to us very interested in our hyperspectral offerings. And so they were super interested in what essentially hyperspectral can do to, improve and widen their possible range of applications and improve accuracies and things like that. So one of the things we were talking about is, improved measurements of kind of more quantitative estimates of turbidity and light attenuation in water. So one of that being is the actual, optical property of attenuation itself, which is denoted as C here. Specifically at 670 nanometers is a very specific wavelength that hyperspectral can provide that allows a really good optical quantitative measurement of the actual light attenuation in water, which is really indicative of the type of particles and substances that are in the water itself. So this here is showing an actual example of an airborne hyperspectral imaging called Avaris NG. And this is over the Mississippi Delta in the United States. And here we have the initial RGB flight line down on the bottom. And as we move up, we use a specific indice called the NDWI to mask out the water and non-water features to create an aquatic map so that we know where to apply the algorithms. And up above that, we see the actual attenuation at 670 nanometers product. And within these this is probably one of the most dynamic and optically complex systems like on the planet. A lot of different sediment types coming in with the inflow. We get, sometimes some really variable phytoplankton blooms and things like that. So a lot of really interesting competing complex signals that we're getting. And using hyperspectral imaging, especially at a really fine spatial resolution that Firefly will be able to provide, we can produce really accurate insights of the type of water clarity and water turbidity, and even potentially identifying types and sourcing of sediment types and things like that. Hyperspectral imaging also allows for improved sunglint correction, which is one of the contamination effects I mentioned earlier. So especially in aquatic systems such as these, where we have really narrow kind of waterways and really tight areas between water and bright kind of land pixels of vegetation or sand and things like that, you get a lot of these really competing signals from the really bright land pixels that I mentioned before that get scattered into the field of view of the sensor. So we can see an example of this actually down here, where on the bottom right in the RGB, we see a very sun glint affected area over on the right, where the water pixels are oversaturated due to the sun glint. And we can see when we train a model with a sun glint correction that we've developed, that we can, without the sun glint correction, we are actually producing way over estimates of the attenuation in the water. Whereas when Hyperspectral is able to provide better sun glint correction, that allowed us to produce much more accurate spatial distributions of the parameters of interest, in these types of areas. Similarly, this is another hyperspectral imaging sensor called HyCO, which was up on the space station for quite a few years. And it was a NASA instrument. And this is an image of Lake Erie, which is in North America, a common place for cyanobacteria blooms that are quite seasonal and could produce really toxic blooms that cause health and public safety concerns. But what Hyperspectral really kind of brings, and what we're excited to bring to TCARTA, is the ability to really accurately distinguish between the organic and inorganic signals. So in this image here on the top row, we see various parameters of phytoplankton biomass, so that being chlorophyll A, absorption of phytoplankton, and the backscattering of phytoplankton. And on the bottom row here, we can see NAP, which is non-algal particles. So this is like the sediment, the mineral particles and detritus. So a concentration of non-algal particles and absorption and backscattering. And what we're really trying to show here is how we're able to disentangle these signals, because as a lot of conservationists and ecologists really want to get down to is actually really separating out that phytoplankton signal from the sediment signal, because that's one of a really, really difficult problem with traditional multispectral sensing. And if we can distinguish those phytoplankton signals, then we can much accurately predict for other kind of more climate and carbon cycling related scenarios. And so I want to expand.
Jeremy, we've had a couple questions come in, if you don't mind. I think there's some pretty interesting stuff that people are asking about. So I'm going to take a brief break for a second. The first one is related to all this water quality monitoring that we're seeing. Just how particular can you get about it for like biological and chemical contamination? Can you actually get down to concentrations, or what do you think the limits are going to be with hyperspectral imaging in this?
Yeah, that's a really good question. The real full potential is still, I think, unknown. Hyperspectral imaging as a whole is still, a pretty new technology. Government agencies such as NASA, European Space Agency have been experimenting with it for a little bit now. But we're really only kind of getting into the golden age of hyperspectral, where we're seeing much higher spatial resolutions and the capability to increase the spectral fidelity of what we're trying to see. So in terms of what, like the limits of what we'll be able to detect in terms of type of chemicals and things like that, chemicals are a little bit difficult, but where hyperspectral is really going to shine is in the differentiation of different phytoplankton types and phytoplankton groups, and as well as even potentially trying to differentiate different sediment mineral particle types. So with that increased spectral fidelity and increased spectral resolution, we could potentially identify various kind of spectral slopes of the different absorption signatures of different sediment types and things like that, different particle sizes and composition of different mineral particles will reflect differently as they absorb and scatter differently. So it's really about how good your ground truth data is as well. Hyperspectral and remote sensing just in general is only one component of the whole picture, which is really complemented with in situ measurements as well. So if you have really good in situ and ground truth data for whatever kind of particular problem you're interested in, that will also, help decide what kind of the limits that you'll be able to do. I never want to say remote sensing is the end all solution for everything in the world. We're always going to need, really high quality ground truth measurements as well.
Absolutely. Quickly before the other questions, someone is asking, what are inorganic signals? Like, what does that mean when you're looking at water?
Yeah, no, that's a good question. Inorganic meaning non-living. So we can separate out organic, meaning essentially the phytoplankton, the living plant-like material in the water that we usually associate with chlorophyll A concentration or harmful algal blooms. Inorganic meaning like the actual the mineral sediment that's usually run off from land or potentially redistributed from the bottom seafloor due to wind or crazy weather and things like that. So that's what I mean. Inorganic is or non-algal particles, people like to call it, are the combination of mineral particles and degraded phytoplankton, non-living phytoplankton particles, dead stuff. And then the algal component or the organic component being the phytoplankton itself.
Fantastic. And one last question before we, move on to the next example. There's still more. We'll get to them at the end, no worries. But for water quality mapping, is there, Dave or Jeremy, I'd love to hear both of your opinions on this. Is there a focus on marine and floating debris? Will there be data that's able to actually observe and tackle that class imbalance problem? Just because, you've got a lot of water and then you have one little floating net. How do you guys feel about that?
Yeah, Dave, you want to go?
Yeah, I can start. Yeah, so that's a question we've gotten quite a bit is, specifically, the topic of ghost nets comes up a lot for us. And currently, because they sit just under the water, typically, they are actually incredibly hard to identify with typical multispectral sensors. Hyperspectral sensors should be able to help identify those better than we can currently. The other thing that, specific to a more, biological thing that we actually are working on monitoring right now is sargassum. It's been a big problem in coastal areas in Central America and then some parts of North America, as there's been these huge sargassum blooms that are washing up on beaches and really affecting tourism in some areas. And so one of the things we've been able to do is actually use some of the more, freely available Sentinel-2 type sensors to use some floating algal indices to identify those and kind of track those with time. But again, there may be other floating algae that we can't really differentiate from at the moment using the multispectral sensors, and that's kind of where that hyperspectral kind of the more spectral resolution is really going to help with that kind of moving forward.
Fantastic. Anything you want to add on, Jeremy?
I think Dave summed it up super well right there.
All right, thank you. I will let you guys continue.
Thanks, Megan. And thanks for the questions. Yeah, keep them coming. So I wanted to show a case study of ours. This is a pixel satellite image from one of our tech demonstrators. This is a level 2A atmospherically corrected image of Utah Lake in the USA, particularly the eastern basin of the lake, which is particularly prone to harmful algal blooms. And hyperspectral imaging really allows us to pinpoint exactly where pollutants are entering the water. And so knowing these sources is really crucial for effective water quality monitoring and for assessing the impact of runoff from surrounding areas. And so by identifying specific points of pollution, we're not only really able to monitor the contamination, but also to understand, how runoff flows through the landscape and revealing potential weaknesses in water runoff infrastructure. And also being able to correlate those pollution sources with algal blooms, such as the cyanobacteria bloom. And this one is identified by estimating the actual specific cyanobacteria absorption feature, which is at 620 nanometers. This is indicative of the diagnostic algal pigments that are within cyanobacteria. And using this information, we can really gain valuable insights into the lake's ecological health and can respond more effectively to prevent further deterioration or public health concerns. And these dense blooms are not really only relevant for public safety, but also carbon sequestration too. So algal blooms are not just pollutants, but they're also contributors to the carbon cycling. And so on the left, we see the chlorophyll A concentration, which as we know, correlates with the presence of phytoplankton. And then on the right, we have actually an estimation of the phytoplankton carbon content, which is derived from specifically that phytoplankton backscattering signal that I mentioned before. That's where you find most of the carbon content is found in that backscattering signal. And this represents pretty much the amount of carbon being captured in the algal biomass itself. And so while excessive blooms are often, really a negative indicator of water quality, they can also capture significant amounts of carbon. So this dual perspective shows how hyperspectral imaging can really quantify both the ecological impact as well of blooms, as well as their role in carbon sequestration, giving us a really full picture of their environmental significance. So popping over to a different theme under aquatic applications, benthic mapping, which is where T-Carta really shines. So I'll hand it actually over back to Dave to chat a little bit more about, how they approach this problem.
Yeah, so one of the things, and Jeremy's mentioned it a couple times here, is that we look at when we're choosing imagery for benthic habitat mapping is the absence of sun glint. That is a big thing that affects coastal remote sensing in general, like Jeremy's mentioned, and then also turbidity is another thing. So we really require for benthic habitat mapping generally clear water. And a clear water column, absent of any kind of extraneous signals. And that's because we really have to be able to see the bottom to be able to, classify the habitats that are there. So for those of you that may not be as familiar with benthic habitat mapping, really what we're trying to do here is classify or take satellite imagery, classify it using ground truth data. That is one thing that we do require typically for this process to get into some of these more differentiated classes that you can see here. Without ground truth data, we can get some more basic classes like sand, coral reef, seagrass if we have an idea of what's there. But to really, get the full potential of this technology, we really do need that ground truth data. And so what we do is we take that satellite imagery. We do create some derived products from it. So we create satellite derived bathymetry, which is one of the main inputs for some of our models, which we'll talk about that in a little bit more detail later. But we use that, the imagery and our ground truth data, and use some sort of classifier model. We use a variety of different ones depending on what we're trying to achieve. We do a random forest, support vector machine, things like that. And then the result is something like you see here in the middle, a pixel-based classification of the habitats on the seafloor. So in this instance, we've got a different variety of biological and also some geomorphological things that we classify. And that's kind of where that satellite-derived bathymetry comes in. We use some slope and rugosity, things like that, that go with that to be able to classify things like the forest slope of the reef. And some different, like I said, geomorphological parts of the habitat. One thing also that comes into play here that Jeremy has also mentioned that we're excited to use hyperspectral for is actually the water column correction, because that's one of the most difficult things to correct for in this process is, if you look at a satellite image, and you can see here in the image on the left, the reflectance or the brightness of the image changes with depth, and it can be very difficult to correct for that. So we're really looking forward to using hyperspectral to be able to do that a little bit more accurately than we can currently. And so once we have a habitat map such as this, we actually reserve some of our ground truth data to check kind of what we've been doing. So here on the bottom it's a confusion matrix, so we can actually look to see how well our classifier performed. And you'll see here, and I'll show it, and we'll talk about in a few different slides. Right now, what we're looking at is we have all the algae grouped into a single class, the seagrass grouped into a single class, and we're hoping to, and will likely be able to break those down into different, more specific species in the future using hyperspectral imagery. Jeremy, if you could skip over to the next slide. So So one of the, you know, a benthic habitat map is really great. It gives you a snapshot of, you know, what's going on in a specific location at a specific time when that image was captured. But one of the powerful things about remote sensing in general, but in terms of habitat mapping, is actually showing changes over time. So we did this project in the Bahamas. We mapped a very large area of seagrass over the Great Bahama Bank. And what we found over a 10-year period from 2010 to 2020 is a massive loss of both dense seagrass and sparse seagrass, you know, over time. So in this specific area of the Ragged Islands here, you know, you can tell from those pictures on the left and the right, and the top, from top to bottom, just how different the seagrass extent was during that time period, and you know, up to a 60% loss of dense seagrass, and a 40% loss of sparse seagrass. And again, this was done with multispectral imagery, but with accurate ground truth data. We're really interested in being able to see if we can actually look at if there may be a specific species that is in decline as opposed to just general seagrass. We do have some pretty high accuracy ground truth data here, so we're really interested in looking at that as kind of a future add-on to this project, because you know, it may be that one of these, there's a specific seagrass that's been more impacted by potential, you know, climate change impacts of, you know, potential you know, warming of the waters in this area. So that's something that we're really interested in looking at and hoping that we can kind of tease out with hyperspectral imagery.
Nice. We actually have a question sort of related to this and also the previous topic that's come in. And we've got a lot of other questions, but I'll make sure we can get through all the different use cases you guys are talking about first. So this one says, you know, I'm interested in applications related to inland aquaculture, specifically shrimp and fish farming. Is it possible to measure animal welfare, things like dissolved oxygen, ammonia content, stocking density, you know, classifications of the farms, etc.? Like how do you see that working out, both with, you know, what we talked about previously with the concentrations and stuff, and also this with the mapping capabilities that you're getting?
Yeah, Dave, you want to start?
Yeah, I can. So we have investigated this in some instances before. You know, we are somewhat limited with the current multispectral technology into what we can actually measure in those systems. So we can measure, like we've talked about before, in terms of some biological parameters that we can look at that are an indicator of stocking densities and things like that. But it is at the current state with multispectral imagery hard to do some of those things. So there is potential for hyperspectral imagery to help there. I don't know, Jeremy, what your thoughts are.
Yeah, I mean, detecting things like ammonia and dissolved oxygen is really difficult without a lot of ground truth data. They don't really produce a distinct optical signature per se that we could really kind of focus on to separate out from the other signatures. So things like that are a bit more difficult. What we can do, though, is, you know, using hyperspectral imagery is derive a bunch of other physiological parameters of the water itself. So being able to identify early signs of pollution and eutrophication that could really affect fisheries and things like that. I have seen some studies about using remote sensing to identify fish stock populations. I have seen that done. Generally more in clear waters where there's a bit more, you know, subtle signature changes, like due to kind of large masses of fish, and they've been able to predict, you know, estimates of stock biomass in aquaculture farms. So I have seen that done. So it's definitely not off the cards. Sometimes you just got to really get creative, and again, you know, with good high quality in situ data, you know, and a lot of things could really be possible.
Thank you very much. And I know we're running short on time, so please continue with the use cases. If we have any time for questions at the end, I will be bringing them up.
Cool. And also, if we don't have time to finish up all the questions, we'll, you know, write out the answers, you know, afterwards, and we can send them out to the group as well.
Yeah, so kind of following on what we were talking about previously in seagrass monitoring, we've looked at a lot of density differences previously at TCARTA. One thing we were able to do recently, which is pretty interesting, is actually differentiate between a few species here in the Red Sea. This took a lot, as Jeremy mentioned. NC2 data and ground truth is always the key to solving a lot of these problems, and then using that in conjunction with the tools that we have. So, in this instance, we were able to differentiate between two different seagrass species. Um, and I will say this is somewhat of a unique thing that we were able to do this. And again, it was mostly attributed to the ground truth information that we had. And we are really looking forward to using hyperspectral imagery to do this as well. And I think we're going to be able to really differentiate those much better than we were able to. This was with 8-band imagery that we were able to do this. So a lot of those subtle differences in the seafloor, specifically in dark habitats like seagrasses and algae and corals, there's very, very subtle differences between those in the spectral signature with multispectral imagery. We've talked about it several times before, but there's different absorptions features for these different species and different benthic habitat types that we'll be able to use that to our advantage in the future to really start to differentiate these in more detail.
Great. Yeah, I'll continue on from there. And I just want to emphasize a point that David had mentioned where hyperspectral is really going to, I think, benefit them is the ability for really advanced water column correction. So that's been really one of the biggest challenges for benthic mapping essentially we have to perform another atmospheric correction. We have to correct for a whole nother medium to get down to that benthic signal, which is probably fractions of a percent of the total signal that eventually hits the satellite sensor. So it's a lot of stuff and information that we have to correct for. So with hyperspectral imaging, we're able to, leveraging the really unique spectral absorption features and scattering properties of water that we can detect, we could really correct for these effects more accurately, making it easier to isolate and really identify benthic features with much higher accuracies than ever before, and now at pretty high resolutions as well. So this is using the PRISM airborne hyperspectral instrument at 5-meter resolution, which is going to be the same spatial resolution as our Firefly sensors. And using hyperspectral sensors, we can really extend benthic classification to ecosystem scale primary production modeling. So primary production, which is essentially the amount of organic matter produced through photosynthesis, and really forms the basis of the marine food web. So coral reefs and algae beds are particularly productive and play a key role in supporting biodiversity. And the middle image here highlights an accurate benthic classification map, and in this case, just distinguishing between coral, algae, and sand, but which are essential for really understanding the spatial layout of these different habitats, which then in turn influences the different primary production rates. So over on the right, then we see in areas of red and yellow indicating higher rates of carbon production, which are vital zones for marine life, and then being able to correct for the water column's impact on the light penetration. Hyperspectral data can really give us reliable measurements of chlorophyll and other indicators of photosynthetic activity. So this capability really has lots of broad implications, and as high productivity areas are also essential for fisheries, conservation, and carbon sequestration efforts. So we see this data being really able to improve our kind of carbon cycling monitoring and accountability as well. And lastly, another big part that TCARTA shines is kind of intertwined with the benthic habitat mapping as well, but I think deserves its own little chatting about because of how important this particular parameter is in kind of global navigation and maritime industries. So I'll let Dave kind of chat a little bit about that too again.
Yeah, thanks, Jeremy. So, we and Jeremy just mentioned it again, but as water column correction, again, it's a key thing for satellite-derived bathymetry. And essentially what we're doing with satellite-derived bathymetry is, relating reflectance of the seafloor to depth. And you can see here, this is a a global map of where we've produced satellite-derived bathymetry to date. And a lot of people, and it is concentrated in certain areas, but luckily with some advancement in algorithms that we've been using, and then technology such as hyperspectral imagery, we're going to be able to expand this even further into more marginal areas. Like these typically that you see here are more clear water areas that we've mentioned before, but we'll be able to extend that into more different categories of waters where there may be more turbidity or more algal blooms, things like that, where we can actually account for those in the water column with the hyperspectral imagery, where we haven't been able to as accurately yet with multispectral imagery. So this is just an example of one of the projects that we've done. So this is in this is in Lake Michigan in the United States. And we are able with satellite-derived bathymetry to get fairly high accuracies when compared with LiDAR. You see here a mean error of approximately 30 centimeters, which is really good. In most cases, the error does increase as we increase with depth. So with satellite-derived bathymetry, we're limited. The theoretical limit's about 30 meters as to where we can see depth. Or get a reflectance signal from the bottom. In practical applications, it's more like 20 meters. That's kind of where we've been able to get in most areas, sometimes down to 20, 25 meters, something like that. But one of the really powerful things about satellite-derived bathymetry is, Jeremy mentioned, is its cost effectiveness. It's really, compared to flying a LiDAR survey, it is very cost effective. And the other thing that it's incredibly useful for is actually filling gaps in surveys or places where surveys haven't been performed in 100 years. We can get depth measurements that are fairly accurate that we can use to fill in those gaps in data that we currently have. And we've done this in numerous places around the world. And so, this is an example, as I mentioned, in Lake Michigan, where we've compared with LiDAR, and we get very high fidelity results. We use a couple different models to do this. We use a radiative transfer method, some empirical methods, and then some also machine learning methods to do that. And all of those in their own way create a water column correction in some sort of, by taking into account the different physics of the water column itself. But again, that's where this hyperspectral imagery is going to really come in to help us do that in a better way than we can currently. And also, I will say again, what we find with satellite-derived bathymetry, especially over dark benthic substrates, seagrass and corals, the depths tend to be overestimated, so deeper than they are in reality. And again, that's because they have some, subtle differences in the spectral signatures are really hard to model with multispectral imagery, and that's where that hyperspectral signal comes in and really can help us differentiate those and help us get higher accuracies over some of those darker areas, especially once we get into the deeper depths that we're not able to currently.
All right, with that, we are getting close to the hour, so I know there's a lot more interest and a lot going on. We'll see about publishing these slides and definitely answering your questions, but I'd like to pass it over to Amy for some final remarks on the webinar, and thank you two very much.
Yeah, thank you guys so much for the informative session. I'm afraid this is all we have time for today. And as Megan just said, any unanswered questions, we'll follow up with responses via email. Thank you all for your participation. Once again, huge thank you to our speakers, Jeremy and Dave, for their presentations, and Megan for moderating the discussion. And of course, a special thank you to all of our attendees for your interest and engagement today. To remain updated with Pixel's progress, please sign up to our newsletter, follow us on LinkedIn, or drop us an email shown on screen. And of course, we want to give a big thank you to T-Carta, and their contact is also shown on screen. And we hope that we'll have more collaborations like this to advance Earth observation solutions in the future. And I guess that's all. Thank you so much for joining us. We hope you have a great day ahead. Thanks, everyone.